is always nice. And I think we have some questions today. So we're supposed to be doing, okay, so at this point, I think the most important thing you really need to do right now is to do the lab. And there are some questions in the lab. I mean, you need to do the questions, but the most important thing you need to do is actually to implement the lab. And the reason is, I think that once you actually implement the lab, like, a lot of this will start to become a little clearer, okay? And it'll be, you'll start to get a sense of why someone would care about any of this, okay? And, because if you don't, when you actually have to put your fingers to the keyboard, you have to actually understand what's going on, okay? So, maybe we could take some time to go over questions today, both maybe homework questions or lab questions, and also, you know, to talk about the lab. I know there's at least some questions. So why don't we do that? Okay? So we have at least one question, right?
Yeah. Yeah. So it probably helps to like view the lab, or I don't know. So I guess I have a question about the iterative coordinate descent algorithm.
Okay.
So the way that it's explained, there's a derivation in the lab, it's like part 4 of the lab, that talks about iteratively updating the estimate of the noise variance, right? And how that is essentially continue to update the noise variance so as to be able to update the likelihood or the estimator, the map estimate of each pixel. But in the implementation, we're told to just choose a noise variance and to not continuously. I guess there's some confusion there.
Yeah. Okay.
Like
so I can switch to the lab on the PC and then answer your question from there. How's that? Okay. So this is get the PD feed. Okay. So
that's right.
So what happens is that. So first of all, okay, let me back up a little bit. So you have the problem you're trying to solve when you do the map estimate is you're trying to minimize this cost function, right? So you can also write that cost function out as in matrix form, but I think people find it maybe initially easier if you just have explicit sums, right? And so this would be just the norm of the error between y. This is the norm squared of the error between the vector y and the vector x, right? And then this is basically okay. So this is a little bit different form, and we're going to kind of learn about this later. But it turns out that that expression x transpose bx can be rewritten in this kind of a form. Under some assumptions. Basically, the assumption that has to hold is if for each I, the sum of g over j is 1. So that's to say, if the sum of all the neighboring weights sums to 1, right, then you can rewrite it this way, okay? So now, okay, so fine. So this is the overall expression. Now, if you're going to compute the map estimate, you want to find the value of x, the vector x, which minimizes this whole thing. So, in addition, but that requires you actually know the noise variance, and this isn't the noise variance, this is the non-causal prediction variance, so it determines the amount of variation you allow, the amount of regularization, right? So, sometimes what happens is that sometimes you know these numbers, like you actually know in your application what the amount of noise is in your sensor, and sometimes you don't, so you need to estimate those parameters as part of the reconstruction process. So, you could actually not just minimize with respect to x, you could also jointly minimize with respect to sigma squared. So if you take, okay, now in this current VAT form, maybe this lab could be rewritten a little bit to make it clear for us a little bit. Actually, I wrote this lab a long time ago. I could probably rewrite it and make it a little clearer. But if you minimize this thing with respect to sigma, of course, it's kind of a silly thing to do because the minimum is going to occur when sigma is infinity, right? Because then this whole term is just 0. But that's only because we dropped some terms. The terms we dropped were that this is the probability distribution, right? So this term here is the negative log of this. So there's this term we dropped here, which is the log of sigma to the n, right? I should actually probably just write that out. So, so if you include that term and you minimize with respect to sigma, then you actually get a closed form result for the solution as a function of sigma. See here, maybe this isn't as explicit as it could be, but if you write out these expressions here and minimize with respect to x and sigma simultaneously, you can actually get a closed form solution for the relationship with respect to sigma. Okay, that's this, okay? And then, so this begs another issue, which let me just go to the document camera form, because this is going to be, come up a lot in everything we do, and I think it's a little bit of an abstract idea. I know from experience that it takes a while for people to get used to this idea, but once they do, then it's pretty straightforward, which is that you have a function. Okay, so you have a function of, say, two things, a and b. And let's say a and b could be vectors. They don't have to be scalars, okay? And you want to minimize this thing with respect to a and b jointly, right? So, okay, so then you have the argmin, that would be, say, a hat, b hat. Is that on the screen? Yes, it is. Good. Okay? So that would be the joint minimization, right? Well, what you can do, so if you want to solve this problem, okay, there's a lot of ways you can solve it. First of all, one thing to point out is that if you minimize something with respect to A and B together, that's the same thing as minimizing with respect to A and then minimizing with respect to B. So what does that mean? It means that if I take this function and minimize it with respect to B, this function is a new function. I'll call it, say, f tilde of A. It's the function which for every A is the minimum of that function with respect to B. So the way to think about that maybe is if you have rows and columns in a matrix, right? If I want to have the minimum value in a matrix, there's a lot of ways I can do it. One way I could do it is I could search through all the rows and columns and just find the minimum. But another thing I could do is this. I could take, for every row, I could find the minimum value along that row, right? So, am I running out of space yet? No. Okay. And then what I could do is for that set of minimums, I could find the minimum. And that would be the minimum, right? It's obvious, okay? That's what this equation here is saying, okay? It's saying if I minimize, for every A I find the minimum B, and then I find the minimum over those, I'm going to have found the minimum, okay? It's sort of not very deep, let's say. But there's another thing you could do, okay? Which is just, you could say, I can take A, okay, and I can make A the argmin over A of f of A, B, okay? So I can minimize with respect to A for a fixed B. Or for every B, I could, okay? Or, no, right. No, for fixed B, okay? And then what I do is I could say, okay, now I'll take the B and I'll replace that with the argmin over B of f of A, B. Okay, now when I get finished applying those two things, okay, and I can actually even repeat it, but I'm sort of, maybe I shouldn't have told you I can repeat it because sometimes I've told you the answer to my next question, which is that if I do this, if I replace A with the minimum value of A, and I replace B with the minimum value of B, after I do that, have I found the minimum? Not necessarily, okay? Because in that case, you're doing something different. Then you have, this is your 2D array. You started at some point, and you traveled until you found the minimum, okay? And then what you did, at that point, now, so this axis here is like, that's the A axis, and this is the B axis, okay? So you travel until you got the minimum, and then you minimize B until you found the minimum. And then you minimize A until you found the minimum, right? You can do that. Well, first of all, you could potentially do a lot of iterations before this process stops, even if it's a discrete grid, okay? And second of all, when it does stop, you're not necessarily at the global minimum. You'll be at a global minimum because you'll be at the minimum value along that row and column, but you won't necessarily be at the minimum of the array. So my point here is that this joint minimization with respect to A and B is equivalent to the sequential minimization of A and B. That's the same. But those two things are different than this, okay? What's different here is this actually is sequential in time. This is not sequential in time. This is a mathematical equation. You know, there's no concept of time in a mathematical equation. Because that's the difference between, in the notation actually in the notes, if we have, we say A equals B, right? That means A equals B, right? But if you say A goes to B, this means you take the current value of A and put it in B. This is a concept of time, right? Because one of my favorite things is in Fortran, they have A equals A plus 1. Does that bother anyone? Tell me that bothers you, please. Let's try this. Does 1 equal 1 plus 1? Oh, maybe we just have, how about 2 equals 2 plus 1? Okay, but if you took like a really big number here, like 10 to the 10 equals 10 to the 10 plus 1, right? Only for engineers. Okay, anyway. No, none of these things are true, right? Because if Fortran, the notation is unfortunate, what you really meant is that A goes to A plus 1, okay? Okay, now, so here you got a sort of a time sequence thing occurring, right? So, now, this thing here is called alternating minimization. So, you have something which is a function of a couple of a number of different things. So, you'd like to minimize with respect to all of them, but what you do is, it's too hard to minimize with respect to all of them. I mean, sometimes you can minimize with respect to all. Let's say, an example is computing the maximum likely estimate of the mean and variance. Everybody went through that calculation at the beginning of the class. It's like a calculation everybody says to do once in their life. Okay? So you first minimize with respect to the mean, okay? And then you take that expression and you minimize it with respect to the variance. So that's this, okay? But often you can't do this, so instead you do this. You take one variable and minimize with respect to it, and then repeat for the other variable and just keep going back and forth. Now, this is called alternating minimization. Alternating minimization, okay? And alternating minimization should be something that's very intuitive, because humans do it all the time, right? You say, you know, like if you want to achieve some outcome, right? So you have like some kind of gizmo, and it has like, you know, some knobs on it, and here's the power meter, okay? Here, okay? And you want to maximize the power. I mean, what do you do? Everybody knows what you do, okay? What do you do? If you don't know how to pass this test, then you fail this course because you're not an engineer. If I gave you a box like this and said, your job is to put the needle on its highest to its highest position, okay, what would you do?
Maximize each independently.
If you took the first knob, come on, I mean, like, I'd be deeply disappointed, okay, if you couldn't do this, okay? You take the first knob and you adjust it, okay, until it's at its maximum value, right? And then you go to the next knob, and adjust it until it's at its maximum value, right? And then you go to the next knob, until it's maximum value, right? Now, are you done? No. You go back to the first knob again and you readjust. Okay? It's like if you wanted something and you had a whole bunch of Purdue administrators, okay? Okay? What you do is you first go to the first Purdue administrator and you say, can I have this? And they say no. Okay? And then you go to the second one and say, can I have this? They say no. Okay? And you get all the way to the end. Okay? And then, can I have this? And you say no. Okay? And then you go back to the beginning and they say no. And then you just keep going around in circles. Right? So now, okay. Alright? So that is the essence of this algorithm. Because what happens is that you have this, I'm going to call it the map cost function. Okay? The map cost function is going to be a function of sigma squared W, okay, and X, right? And it's equal to, I'll actually write it out. I should have written it out. Okay, it's going to be 1 over 2 sigma squared. I'm going to leave off the W because it's too much trouble to write. Okay? And then it's going to be the norm of y minus x squared, right? And then it's going to be it's going to be it's going to be it's going to be plus, so, okay, I'm screwing this up, so hold on, I can't put this steps in my head. So the probability distribution, P of y given x, is going to be 1 over, it's going to be 2 pi to the n over 2 times 1 over sigma to the n, right, times the exponential of minus 1/2 the norm of y minus x squared. Okay? Does everybody know where this came from? This is the conditional distribution of the y given x, given that you assumed that you added white Gaussian noise to x. Right? And this is just, and then I've left off the sigma squared here. Okay? So if I take the log of that, I get, if I take the negative log, so the minus log of P of y given x, right? That's equal to 1/2 over sigma squared, the norm of y x squared, okay? And then this is plus n over 2, and then this is the log of 2 pi sigma, like that, right? Yes. Thank you. Right? So now I can take this over here. So this is going to be n over 2 times the log of 2 pi sigma squared, right? and then this is plus x transpose dx, right? Now if I minimize this, so now I can do alternating minimization. So if I minimize this, I can take the arg min over sigma squared, right, of c of sigma squared x, right? And it's going to be equal to what? Well, you can minimize this expression with respect to sigma squared. Has everybody done that? That was like an exercise in the first section, and it's something everyone should do in their lives. Okay? Do you want to actually do that? Everybody knows how to do that? Okay, if you don't know how to do this, you should do it. Okay? It's like a really simple calculation. You just differentiate with respect to sigma squared, and you set equal to 0. And what you're going to get is what? You're going to get that it's 1 over n of the norm of y minus x squared, where n is the dimension of y. Okay? So basically you're just saying, oh, well, the variance, the maximum likely estimate of the variance is going to be just the average squared error. Alright? So, but what this means is that when I make this update of sigma, this cost goes down. Oh, one thing that's very important to understand is that when you're doing this alternating minimization, when you minimize with respect to one quantity, this is a monotone decreasing cost. So if you plot the cost function here, every step it goes down. Can it go up? If it goes up, what does that mean? So at every step I'm minimizing the cost. Okay? So if I have this thing here, okay, so coming back to the watt meter thing, okay, I adjust the first one to maximize, or let's say I'm minimizing. I adjust the first to minimize, and the second. At every step, does the meter ever go up? No, because I adjusted it to make it go down, okay? That was my criteria. So if it went up, what does it mean?
You're done. Well, you did it wrong.
I did it wrong.
Yeah.
Yeah. Your answer is correct in the sense that if the only thing I can do is go up, I'm done. Okay. But if it actually went up when I was done, I made a mistake. I turned the knob incorrectly, right? So this can't happen. It can't happen. It can only go down. Okay. So now what I'm about to tell you is very profound. Okay. But you won't understand how profound it is. Okay. It's like you've gone to the mountain. Okay. And Buddha said, or I'm sorry, I don't mean to offend your favorite. Okay. I'm not getting into more trouble here. Okay. And an oracle said, okay. An oracle said, my child, eat a peanut butter and jelly sandwich. Okay. And you said, Drew, that didn't seem very profound, okay? And then later on you found out that this was the answer to the meaning of life, okay? Okay. So now, I'm about to say something very profound that's going to not sound very interesting, okay? That if this thing goes up, you have a bug in your program, okay? Okay, I'm going to write this down, okay? Because it is so profound, okay, that you're going to you're not going to remember it otherwise. I say, if the cost goes up, you bug in your program. Okay? So now, what happens typically is students will go, but what if it just goes up a little bit? Okay? It just went up a little bit, okay? And I've been working on the program for a long time, okay? And I'm really tired. But it just went up a little bit, okay? So what's the answer? If the cost goes up, a bug in your program. Small bug. A small bug, okay? But guess what? There is no such thing as a small bug, okay, in these programs, okay? So it's really funny. I've known people who are like super duper, Cheetos eating, Diet Coke slurping, like non-sleeping computer software jobs, okay? But they can't write these programs, okay? They can write, like, compilers for, strange operating systems in, ancient languages, but they can't write this program. You know why? Because it's a little bit different technique, okay? But this is the golden rule of, and there's a different programming style. So one thing you will get out of this course if you successfully complete it, but along the way, the advantage of the people who are far away in TV land is that I don't have to worry about you tracking me down, okay, and assassinating me, okay? Because it can be extraordinarily painful, okay, trying to debug your program, but you have to kind of go through it. I don't know of any other way to teach it, and I'm happy to try to answer your emails and sympathize with you and feel your pain, okay? But in the end, you just got to do it, and you kind of check that the cost only goes down, okay? If it goes up, it's wrong, okay? So let's say that the cost at times whatever is 1.3572694 times 10 to the minus 5, okay? And then at the next time it's 1.3572783 times 10 to the minus 5, okay? Guess what? You have a bug. Because this is, 1, 2, 3, 4, 5, 6, okay? That's 6 digits of precision, okay? What's the precision on a modern processor? It's 64-bit float. Double precision floats are 64 bits, right? You can actually look it up. We can look it up. But I think the Mantissa is something like 10 to the 12 or 15. So if you have like an error in the 10th significant digit, it might be machine error, maybe 12, I don't even know. Okay, but if you got it in the 5th or the 6th, you got a bug. It's very disheartening. But that's, okay? So what you have to do is you have to compute the cost function, and you have to check, okay? So what can typically happen if your cost has gone up? It's because you have either you've done something wrong in your evaluation of your cost function, or you didn't do the update quite correctly. Somewhere you might be on the boundary, you didn't do the update correctly. There's a lot of different things, okay? But this is how you debug the program. Okay, so getting back, this is the expression you have. Hold on. Okay, so this is the expression, that's the minimum, okay? And then what you do is you say, okay, I can minimize x. I did this argmin for the, over x. For the x, I don't need this term because it's not a function of x. So I just put 1 over 2 sigma squared norm of y minus x squared plus x transpose dx, okay? And so this is the part, okay, that we've been talking about here. But both of these steps will make this cost smaller, okay?
So, that last cost function that you wrote, so that would be first you're minimizing with respect to sigma squared, and then you're minimizing, so you're not jointly minimizing, because if you jointly minimize, then you'd minimize.
Right.
Okay.
So even though this could be a global minimization, this is a global minimization with respect to sigma, and that could be a global minimization with respect to x. When you go back, sigma will change again. So you have to do this alternating minimization thing. Now, one thing I'd point out in the notes is that when you're minimizing alternately with respect to these two, you could also do the minimization of this cost function. You could actually take this cost function, you could define a new cost function, we'll call C tilde of x, which is the minimum over sigma squared of the sigma squared x, right? You could actually, so we have this joint cost function in sigma squared x, you can actually minimize analytically with respect to sigma squared and plug that in, and you'll get a new cost function, okay? And that new cost function turns out to be kind of interesting. 1 over n over 2 log the norm of y minus x squared plus x transpose dx. So you say, well, where does this come from? Well, when you compute the well, just believe me. I mean, if you work through it, what'll happen is you take this expression here and you plug it into that expression, right? Actually, it's plus a constant. Okay. If you plug this into that expression, what happens is that this expression cancels with that. You get 1, and then so you get 1/2. Okay. And then I'm sorry, you get n over 2. And then, but that's a constant. And then here, this plugs into that, so then you just get the log of this, okay? And any multiplicative factor in the log becomes an additive constant. Right? Yes.
So the joint minimization is equivalent to finding C tilde and then minimizing C tilde with respect to x, right?
Right, the joint minimization would be equivalent to minimizing this with respect to x. And this is kind of a harder minimization problem in a sense because it has a log, so it's not convex. It actually has the properties of a convex function, but it's not quadratic, okay? It's not a convex function, but it's sort of it's well behaved, but it's not quadratic.
So we're doing the alternating minimization because it's easier?
Yes.
But so in the lab, we are not minimizing with respect to the noise variance because it's assumed that we know it, right?
Yeah.
I think you just so that's worked. We don't have
making it easier.
Oh, okay, yeah.
For some reason, I inserted that little thing into the lab because at that moment I was feeling a bit overzealous, and I decided that I should teach you that, but maybe I overreached a bit. But anyway, we had a nice discussion here. But one of the things that's good, I mean, aside from the fact that that's a useful technique, I think the important thing is this. The really important take-home message is that when you're doing optimization and you have a lot of different variables you're optimizing over, that you can jointly optimize over them, but often that's hard. So sometimes what you do is you do alternating minimization, which means you minimize with respect to one thing and then the other, and then you repeat. And now, in the most extreme case, each pixel can be its own coordinate, its own variable. You can first minimize with respect to one pixel, and then the next, and repeat in sequence, okay? When you take all the pixels and you line them up, okay? So you have f of x1 all the way to xn, right? And you minimize with respect to the first and then the last, okay? So what you do then, you just say you say the minimum, you repeat, and you say for I equals 1. Okay, hold on a second. Well, okay, I'll do it like this. Repeat, and then you say for I equals 1 to n, right? Okay. You say, you take x of I and you replace it with the arg min over x of I. Now we can do f of x1 through to the xi through to this xn. Okay? You see? And now, so what you've done is you've done an update of every pixel to like minimize the watt meter, okay? And then you repeat over all the pixels. That's iterative coordinate descent, okay? So it's like a sequence of optimization. Now, okay, let's see. What else do I want to say here? And then the question is, how do you actually do this optimization, right? Now, and that's what, okay, to actually do this optimization, by the way, it's important to understand that all the other pixels remain constant when you're updating a single pixel. When you're doing this method, okay? So, yeah. Do you have any more questions about the lab, or should I just sort of pick up on the notes at this point?
I have one more quick question.
Yeah.
So, in that same section, I think it's section 5, I think we talked about this briefly, but we talked about like the ICD being it's a monotone decreasing sequence.
Right.
Right? And I think that's fairly easy to show. But then how do you show that it's bounded below? I guess that might be
you look at
fairly
the
easy.
cost function, right? All the terms in the cost function are greater than or equal to 0.
Okay. Oh, okay. All right.
Yeah.
So it's
Everything's
really
easy once you know the answer.
But that's all we don't have to get too, if you get really mathy about it, or no, that's it?
No.
Okay.
I mean,
right.
you'll find that a lot of the questions I ask are really simple.
Okay.
Or at least I like it that way. It doesn't always work out that way. But, yeah, so I mainly just want you to observe sort of the obvious. Because, doing this stuff is really, it's kind of it's a cultural thing, You have to get to a certain way of thinking, I have found, And it's just a different way of thinking about the problem. So, yeah, so after you do this lab, I think you'll find that it's a lot easier to understand. So, basically, this update equation, one way of thinking of this update equation is it's just like, well, I just calculate this and that's what I do, okay? But a better way of thinking about the update equation is that you're taking one variable in this set of n variables, each pixel in the image, and you're just optimizing with respect to the value of the single pixel, okay? And when you do that, this is the equation you get as the result. All right? But if implementing this update causes this cost function to get bigger, then you got a problem, because you've done something wrong. Now, this is not the complete cost function. Why? Because we dropped terms that don't depend upon the pixel xi. We don't need those, because those are just constant, right? So over here, this is the complete cost function, but if I minimize it just with respect to one pixel, I only have to worry about those terms. Okay? So, I mostly want you guys to understand these basic ideas. Right? All the little details you can go through, but I want you to understand this basic idea, okay? Any other questions on this? Yeah.
What's the exit condition when we are minimizing two variables alternating?
Yeah. So in general, you won't converge. I mean, it depends on when you remember. You won't reach a point where okay, one criteria you could set would be when nothing changes, okay? If that's your criteria, for a lot of problems, you'll never stop, okay? Because what'll happen, it'll be like you're in a, well, okay, we're going to talk about this in a little bit, but this is an optimization, so we're talking about the gradient descent, and I have these figures, and you can look at them. But basically, this is like we're doing the minimization or maximization of this function. I could have said, well, I'd rather think about it as the minimization of 1 minus this function, but it's hard when you draw this function. It's hard to visualize. It's easier to visualize this way. Okay, so I drew it the way that was easier to see the shape of the function. But we're really doing 1 minus that, and we're doing minimization. And, okay, so what happens here is that this is, the first A is, well, these are gradient descent, okay? So this just shows the gradient descent. If you set the step size too small, you just converge very slowly, okay? How many iterations you found? It's, 100 iterations, so the convergence stalls, basically. If you went forever, eventually you would get there, but it's very slow. And here what happens is that, well, you get pretty reasonable convergence, but here it's oscillating. Remember I said if you overshoot, you oscillate, okay? Okay, so fine. But, hold on, there should be some more figures here. Oh, here it is. So this is coordinate descent. This is steepest descent. So this is gradient descent. What we haven't talked about it yet. We're using a line search. Okay. So along each step, you take the optimal step, and it converges pretty quickly, but it's still not getting exactly to the minimum. Okay. But the coordinate descent, you just keep iterating back and forth. So you won't ever get there. You'll just get asymptotically closer. There are exceptions. There's an algorithm cognitive gradient, which we'll mention here, and it actually has convergence to the exact solution in n steps for a quadratic problem. Or if the function is discrete time, you can hit a local minimum and just stop. But usually you have to set some sort of stopping criteria. So the stopping criteria is an art in itself, because you don't know exactly how close you are to the global optimum. It may be that a small change in the cost. In general, it's a really bad idea to use the change in the cost to determine when to stop. Because the good news is you have a very small change in the cost, but a large change in the value, okay? So, usually what you do is it's based upon how much the actual value change the degree just is. But, that's kind of, it tends to be application specific. For you, just run it, for a while until, plot the curve and look and see when it looks like it's kind of converged. For now. I mean, that's not a solution for the real application, but any other questions on this? So, if everybody started the lab, then? Okay, try to start the lab, because I think you'll have a much better understanding of what we're talking about when you start the lab, okay? Let's see. Okay, now, so we talked about convergence. Okay, I talked about the frequency analysis of gradient descent. So line search, you'll need to read this. I won't go through this in a lot of detail, but basically, so line search is very important. So what happens is that you have some sort of cost function, right, in 2D. It looks like this, okay? So you calculate some direction in which you want to do the update. This is where you are currently, and you calculate the direction that you want to do the update. And then what you do is you say, oh, well, I'm going to search along this line, and along this line I'll find a value at which the cost is minimum. So what happens is that you have the function, you have the current value of the function, we'll call it xk, right? And then you have plus alpha times dk. So this is the update direction, and this is the size of the step. So what you can do then is you can plot the function like this. This becomes alpha axis, right? And the function looks like this. Okay? Now you say, well, that's pretty simple. All I need to do is find the minimum, so I find the minimum and I'm done. And this is alpha star. Okay, but there's a problem. The problem is that for me to plot this curve like this, I'd have to evaluate the function at 100 points, right? Well, every time I evaluate the function at 100 points, evaluating the function is very expensive computationally, because that function is what? That function is this crazy thing I'm minimizing to start off with, right? Here's the crazy thing I'm minimizing. It's this function right here. Okay, it's this function right here. So every time I evaluate one point on that line, I have to evaluate this whole function. And this is big because I have to do the forward projection, I have to sum over these variables. There's a lot of computation. So doing this line search could be very expensive. So the question is, well, how are you going to do the line search efficiently? This thing is called a line search. Because you're searching along lines, okay? So it's very important. It's the core computation that occurs. There's two fundamental computations that occur in most optimization algorithms. Picking the direction and doing the line search, okay? By the way, if you have a quadratic function, you can take anything as far as up to 2 times alpha star, and you're okay. Because usually, if it's quadratic, then it's like you're skateboarding, right? You shouldn't go up higher than you started, okay? So it's a symmetric function if it's quadratic. So, if you take a step that's bigger than the line search tells you, that's called over-relaxation. And if you take one that's smaller, it's called under-relaxation. And sometimes those are good things, because doing the line search seems intuitively favorable, but in practice, it's a greedy algorithm, so it might be better to do something that either takes a bigger step than necessary, either undershoots or overshoots might be good, okay? Now, doing this line search is tricky. In the quadratic case, there's a closed form expression for the line search. Okay, and this is the solution if you're moving in the gradient direction. If you're not moving in the gradient direction, if you're moving in some other direction, then the most general expression for the line search is a little bit different. But the key point is this: that if you have a quadratic optimization problem, the complexity of computing the line search update step is about the same as the complexity of computing the gradient to start off with. So the line search basically doubles the computation. It's depending on there's various tricks you can play, but it doesn't ever do anything more than double the computation, okay, for the quadratic case. If you have a non-quadratic optimization function, then the line search could be very computationally expensive. It could be much more expensive than finding the actual direction of update. But the most important thing is you just need to understand there's this concept of line search, and it's important, okay? And when you implement it, it can be advantageous. And then the next section is coordinate descent. And coordinate descent, you're going to read this, okay? We're out of time. But basically, coordinate descent works by doing line search equal one coordinate. So you can go through the expressions for the update, and next time maybe I'll talk about this a little bit more, because there's a clever sort of trick to doing the update which makes it computationally efficient. And I'm going to just say hello, okay? Hello, goodbye. Okay.